Alright, so let's start with a couple easy examples. Let's use the truth table to show that the following equivalences are equivalent. Alright, so let's say not P and Q. So this is the negation of P and Q. And we're going to show that that is equal to not P or not Q. So we're just using a truth table to compare these two. So we're gonna put our P and Q. We're gonna write it out: true, true, false, false, true, false, true, false. That looks like one of those dishonest answers. All right, so P and Q, P and Q, T and T, true and true is true. True and false is false. False and true is false, and false is false. Now, not P and Q, that's the opposite of these. So this is false, true, true, and true. So now, not P is just the opposite of this. The opposite of this column right here. So that is just false, false, true, true. And not Q is the opposite of this column. That's true, false, true, false. So it's false, true, false, true. And now we're comparing these with an or. So or. False or false is false. False or true is true. True or false is true, and true or true is true. So we've proven, because this is the same as this, that these two statements are equivalent, and we did it using a truth table. Let's do another one. Just put that off to the side. I'll put it over here for now. Let's say not P or Q is equivalent to not P and not Q. Not P and not Q. And remember, all you're doing with this negation is you're changing everything on the inside. So P becomes a not P, or becomes an and Q becomes a not Q, which is the exact same thing as we right there. So not P or Q, well, we're just going to build a truth table. Now, you don't always have to do this. It's just to get a solid understanding of how this works. After about maybe 10 or 12 hours of working with truth tables, you'll never need to work with them again, because this will all become second nature. So P or Q, it's true, true, false, false, true, false, true, false. And P or Q is true, true or false, that's true, false or true, that's true, false or false, that's false. Not P or Q, that's false, 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 true. Now, not P, false, 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 true, true, false, false, true, true. Not Q is false, true, false, true, false, true, false, true. Now, and false and false, that is false. False and true, that's false. True and false, that's false. True and true is true. So, once again, we have compared using a truth table to prove that these statements are equivalent. We got time for just one more. All right, let's see. Let's do dark red. P implies Q, and that's equal to, we'll do dark purple, not P or Q. This was the tricky one. So I think we actually did this one in the earlier part of the video, but so we see we have P implies Q right here. That's to say that this truth table evaluation will come out to be the same as this, so we don't even have to do this one. But we can go ahead and just write it out like we would. Let's see, actually we could leave that right there. P, Q, so this is true, true, false, false, true, false, true, false. P implies Q, true, false, true, true. That is just true, false, true, true. We just took that right from there. And now, not P is the opposite of this. So it's false, false, true, true. Let's do that in white. False, false, true, true. And Q is the same thing as this, so we don't even have to rewrite it. We can just copy and paste it right there. Now, false or true, that is true. False or false, that's false. True or true is true, and true or false is true. And as you can see, the method has upheld. Once again, these two have proven to be identical. So what does it mean that if the boy does his homework, then his mom gives him ice cream? To say that the boy does not do his homework, or mom gives him ice cream. Because really, there's only two ways this statement can go if mom's being honest here. Either he does his homework and he gets the ice cream, or he doesn't do his homework and he doesn't get the ice cream. The not P basically just says that if he chooses this, then something is going to happen. And if this happens, that's because he chose the opposite of this. So it's either this or this, but they're both evidence of this statement right here being upheld. So that's why they're equivalent. And we're going to use this a lot when algebraically deciding, you know, if a statement is equivalent to another statement, and it's going to help us out a lot. This equivalency right here. So we'll see some trickier problems in the next video.